Welcome to section 3.4, bounded inverses. So we'll give a condition equivalent to the inverse of a bounded linear operator being itself bounded. And remember, bounded linear operators are continuous linear operators. So this covers continuity of the inverse as well. First, a definition, something a little new about bounded below. A linear operator T from one norm linear space to another is bounded below if there's some constant K such that for all unit vectors X, we have the norm of T of X greater than or equal to that quantity K, or positive K, by the way. This deals with unit vectors, so we can generalize it a little bit, playing some tricks with normalization of vectors, and draw a somewhat broader claim that if T is bounded below by K, and if X is any vector, well, any non-zero vector, then we could simply normalize that vector and get T of X divided by its norm. That's T of a unit vector, so we'd have the condition that the norm of that would be greater than or equal to K. Of course, linearity allows us to bring that 1 over norm of K outside the transformation and outside the norm by the scalar property of norms, and then cross multiply. So we can draw the conclusion that bounded below can also be expressed as the norm of T of X is greater than or equal to K times the norm of X for all vectors X in the space, not just unit vectors. This last conclusion, of course, holds for the zero vector as well. So we can say for all vectors, we get this type of behavior. And in a discussion of T inverse, of course, T itself has to be one-to-one, has to be injective. And here's the one result from this section. Theorem 3.6 says, given an injective transformation T, a bounded linear transformation from X to Y, for which both normed linear space X and normed linear space Y are in fact Banach spaces, so they're complete Banach spaces, then the following are equivalent. T inverse is bounded, is equivalent to the condition that T is bounded below, and in turn those two are equivalent to the condition that the range of T is closed. So R of T is a closed set in Banach space Y. The proof, not too complicated. Okay, first we'll prove that 1 implies 2. We'll show 1 implies 2, 2 implies 3, and 3 implies 1, and that'll take care of the equivalence claim. So 1 implies 2. T inverse is bounded. Well, if T inverse is bounded and the norm of T, say, equals constant K, something finite, of course, by the boundedness condition, then if we take any unit vector in Banach space B, we know by note 2.4.a that 1 is the norm of this vector, T inverse times T. This would be the identity, so we can insert that. Note 2.4.a tells us that when we apply a transformation, in this case T inverse, to a vector, what we get is in norm less than or equal to the norm of the transformation times the norm of the vector. It's a little fuzzier here because the vector we're dealing with is the vector T of X instead of simple Y vector, for example. But this is what 2.4 gives us. We pick up the inequality in the vector norm here. We've used it several times. And we said the norm of T inverse is K, so we get a K T of X over here. Quick comment, we couldn't have the norm of this this linear transformation. We couldn't have the norm be 0. We were dealing with T as injective. T is 1-to-1, so T inverse is 1-to-1. And we can't have a norm of 0. And we could have a linear transformation that maps everything to the 0 vector. But then we don't have an injective mapping, and so no T inverse would exist. So we can conclude that this T inverse is not the 0 vector. And so k is not the zero scalar. So we can divide both sides by k is what I'm trying to get out here. So we'll take the norm of t of x, divide both sides by k. Norm of t of x is greater than or equal to 1 over k. This was done in terms of unit vectors x. We chose the x to be a unit vector. So what we get then is that the norm of t is greater than or equal to 1 over k, and t is bounded below, as claimed. Actually, I guess we get it straight from the definition of bounded below. It was stated in terms of unit vectors. So t inverse bounded implies t bounded below. Next, let's show 2 implies 3. T bounded below implies the range of t is closed. So t bounded below, we'll use that. We're trying to show r of t is closed. We'll show ultimately that r of t equals r of t closure. So let's start with an element of r of t closure. We'll show that's an r of t using this information of t is bounded below. All right, if y is an element of the closure of the range of t, that's a closed set. So we can find a sequence x sub n of elements of x such that t of x sub n converges to y. So for any point in the closure of a set, there exists a sequence of elements of that set. It's the t of x sub n's that are elements of the range that converges to that point. Theorem 2.2.8 part 3, maybe we look at that real quick. I got 2.2 in the background. Let's see if I can find theorem 2.2.a. There it is. Part 3, x is in the closure of set A if and only if there's a sequence of elements of set A that converges to x. So that's what we're doing here. Set the set as the closure of R of t, and here's the sequence that converges to that element of the closure of R of t. So t of x sub n converges to y. By the way, this is happening in Banach space y. The t values are in y, so the vector y itself is in Banach space capital Y. So t of x sub n being convergent must be Cauchy. Remember, Cauchy sequences are always convergent, follows from the triangle inequality. And so we just noted in this section, the norm of t of x is greater than or equal to k times the norm of x. That's what we get when dealing with a transformation that's bounded below. This is our observation that we don't have to have unit vectors, but this is a type of inequality we get. So this is where we're using the hypotheses of t is bounded below. Some such positive k exists. So let's look at t of x sub n minus t of x sub n. For any m and n, a natural number, we have the norm of that difference. Well, that's the norm of the transformation using the linearity of t here, t of x sub n minus x sub n. So we've got t of a vector, norm of. Hey, when you have t of a vector, norm of, that's greater than or equal to k times the norm of the vector. So here, instead of a single x, we've got an x sub n minus x sub n. But apply that property, the bounded below hypotheses, to conclude this is greater than or equal to k times the norm of x sub n minus x sub n. All right, now the t of x sub n, that's a Cauchy sequence because it was a convergent sequence. So that means for all epsilon greater than 0, if m and n are sufficiently large, then this norm can be made less than epsilon. Well, hey, if this norm is less than epsilon and this stuff here is strictly, well, is less than or equal to what we have over here, if you can make this small and k is a fixed constant, then you can make this small by making m and n sufficiently large. In other words, since this is a Cauchy sequence, the x sub n's are also form a Cauchy sequence. So Cauchyness of t of x sub n implies Cauchyness of the x sub n sequence. So x sub n is Cauchy. It's Cauchy in Banach space x. in a Banach space, so there's some of the Banach space hypotheses used there. In a Banach space, Cauchy sequences converge, so the x sub n sequence converges to something, call it x. All right, so we went through all of this to get from the range back to the domain, so we can use the hypothesis concerning, as we've used the hypothesis of T bounded below. We need to get back to the X space so we can apply the transformation. So we've got T bounded, I mean, that's hypotheses. We considered T as a bounded transformation. Bounded transformations are continuous. Theorem 2.6 gives us continuity of bounded transformations. That we've used several times as well. So if we look at y up here was defined as the limit of the t of x sub n's. So we get y equals the limit of the t of x sub n's. We can take that limit inside that transformation because it's continuous. And the limit of the x sub n's we've defined as x over here. So we're getting this y equals t of x. We went back to Banach space x and found an x which is mapped to y. Okay, well then that y is in the range of the transformation. So we've shown if y is in the closure of the range, then in fact, y is in the range itself. In other words, the closure of the range is a subset of the range. Of course, the range is a subset of the closure of the range. So the conclusion combines to give us that the R of t, the range of t, and the closure of the range of t are the same thing. In other words, R of t is closed, as claimed. So that takes care of 2 implies 3. Now we want to show closed range implies T inverse is bounded. So suppose R of t is a closed subset of y. Then, by the way, R of t is a closed, did I say it correctly? Suppose R of t is a closed subset, so topologically closed. We want to show a different kind of closure here, that it's closed under linear combinations. R of t is a closed subspace of y, that is, it's a closed under linear combinations. Since if we take y1 and y2, elements of y, this implies there exists x1 and x2 in x with t of x1 equals y1, t of x2 equals y2. Choosing, we're taking those from the range here, since that's what it means to be in the range. So if we take a linear combination of these 2 elements of the range, then we get that they correspond to a linear combination of the x1s and x2s when t is applied to them. So if we take a of y1 plus b of y2, that's the same as t of a of x1 plus b of x of 2. Apply the linearity, bring the scalars out front, and you'll have a t of x1, but t of x1 is y1, so that gives us that. The b comes out front, t of x2, but t of x2 is y sub 2, and that's where that comes from. So we've got closure of the range under linear combinations. So that's the subspace claim. The hypotheses are closure in a topological sense, a closed set, as we addressed in the previous part. So we got ourselves a closed subspace of a Banach space. Theorem 216 told you that closed subspaces of Banach spaces are themselves Banach spaces. So that's the reason to address the subspace part, but a closed subspace of a Banach space is a Banach space. Do I have that sitting in the background close by? I don't think I do. I do not. So let's not go looking for that. It's out there somewhere. But we've got then that R of t itself is a Banach space. So it's complete. Let U be an open set, subset of X, which is open. Then T inverse of U, that's T of U. We get this equality. So what we have then is T applied to U when we look at it, we want to consider inverse images under T inverse. So that's why there's all the inverses here. But we've got T of U, that is T of an open set. And we know by the open mapping theorem that if we have a bounded transformation, which T is an element of the bounded transformations, and if it is injective, one-to-one, then T of U is open. Now this I have in the background. Let's go look at this. So the open mapping theorem requires, it was here, there we go, given, so it's given onto T, so surjective, so I don't need the one-to-one that's there, given surjective and onto mapping, and we're going to treat T as mapping onto its range to use this. T bounded transformation from X to Y, where X and Y are both Banach spaces. If U is open in X, then T of U is open in the space over here. We'll replace this with the range of T in our discussions, and that's how we'll get the onto-ness. So back to the proof. So we get T of U is open, well, open in R of T, as we said. T is bounded and it's onto its range. Every function is onto its range. So we have to go to that space to apply the open mapping theorem. So what we have then is inverse images of open sets under T inverse, with respect to T inverse, are open in R of T. Right? So I'm treating inverse images of open sets. So that gives us inverse images of open sets under T inverse are open in R of T. That means T inverse is continuous. Let's go find note 2.2.c. It says, or alleges at least, exactly that. 2.2, we've already seen this. Let's scroll up a little bit. Note 2.2.c says, in senior level analysis, you see that continuity function is continuous if and only if inverse images of open sets are open. So that's what we've established. We're claiming that as in senior analysis, this holds, and the setting of normed linear spaces as well. That's what the note was about. We've shown inverse images of open sets are open under the mapping T inverse, allowing us to draw the conclusion that T inverse is continuous. But remember, theorem 2.6, we have a continuous linear transformation if and only if we have a bounded linear transformation. If T inverse is continuous, then T inverse is bounded on the relevant range, on the set into which it maps, which is the range of T necessary to get the onto-ness earlier. So T inverse is bounded on R of T. And that's where T inverse is defined on the range of T, so that we get that T inverse is also a bounded transformation. And that's what part one claims. So there's the three implications. One final observation, it's just a special case of this. Let's actually read this, and then I'll make the fonts smaller and see how it follows immediately from the previous result. It's called a bounded inverse theorem. So this is the one that got the name. Given a bijective transformation T, so now we've got one-to-one and onto with X and Y, both Banach spaces, the claim is T inverse is bounded. So bijection between Banach spaces has a bounded inverse. Bounded bijection. All right, so all we got to do is go up here, actually it says below, and simply replace the range of T with Y itself. I mean, the range of T is Y if this is a bijection. So we simply get Y here, And then we have that T inverse is bounded on the set on which it's defined, the range of T. Hey, the range down here will be all of Y. So T inverse mapping Y back to X is also a bounded transformation, telling us that if we consider bijections, you got a bounded linear transformation to X from X to Y, then its inverse, which exists because we got a bijection, its inverse, which maps Y back to X, now that the range is the whole space over here, T inverse is defined on all of Y. Then T inverse mapping Y back to X is also a bounded linear transformation. The linearity is no big deal. The boundedness takes a little bit of this theory. And that's the story of bounded inverses. The next thing we'll look at is we'll define and deal with closed transformations. So I will see you in section 3.5 shortly. Have a nice day.